Hey guys, I just want to do a short video to sort of talk about this CNC router I made. Yeah, so I'm just going to bring it a little closer and tell you about it some. I'm going to try and cut this down. We'll see how that goes. Alright, so, let's do a little closer. Yeah, so, hopefully you can see everything alright. I'm doing this on a GoPro right now, so it's sort of, I don't really know what you're seeing, but it should be decent. So, this is my 3D printed CNC router. Well, it's partially 3D printed. The blue stuff is 3D printed. This stuff, this like, it's kind of square stuff is aluminum tubing. And then like this stuff is some sort of steel. I'm not sure. But anyways, this is a 3D printed CNC router. It was not designed by me. It was designed by Ivan Miranda on YouTube. I'm gonna try and post his channel and then his plans, the plans that he posted in the description. Yeah, because it's really awesome and you should at the very least check it out. I'm not saying you should build it. But yeah, so a CNC router is, I mean, there are two parts. So CNC is kind of just a type of machine. So it's like, it just takes commands from a file called G-code and then sort of moves around accordingly. It's kind of vague because you can make a lot of things CNC, but the router bit, this is just a router. And it's basic, it's sort of similar to a drill, obviously it's very different, but there's a little spinny thing down here that'll cut stuff. So it moves around pretty precisely with instructions from a computer and cuts stuff. That's sort of the very broad overview of what's happening. And now I'm going to talk about how it does that. So after this, I am going to go on the computer, sort of show you the workflow on the computer side of things. But essentially, the end result of the computer work is a file that's called G-code. And G-code is instructions that the machine can understand. And so, you might be like, well, how does that work? So, I have a USB cable here. I have a program on the computer. I use Universal G-code Sender. There are so many out there, though. And essentially what that does is it sends the G-code to the electronics. And that sort of has it programmed in so it knows, like, if I tell it move 10 millimeters to the right, this guy knows I have an Arduino in here, and that Arduino knows I have to do this motor for this long, this much power, all that stuff. It can do that. So it takes those instructions and it's like, okay, I know how to make that happen. And so sort of how do we get there? Well, I have, this is sort of the AC side of things. So I take power from the wall, put it in, it goes through an emergency stop. So if that emergency stop is triggered, nothing is on. The router can't be on, the electronics can't be on, nothing is on. So right now it's closed, but I could like turn it on or whatever. Do that. Then that goes, it gets split. So one side of it goes to this. Let's see if you can see that. I'm not sure if you'll be able to see this, but it's just it's like a normal plug, and that plug goes into the router, so that if I was to hit that button, the router would get shut off. This is like sort of a panic button. It's called emergency stop. And then the other side of the power out, or power in, goes to a power supply. And so I basically just take that normal wall power that you have at home and then make it 12 volts DC. And that 12 volt DC can go to the Arduino, and then that Arduino will send it to all the motors, to these like limit switches and stuff, all that good stuff. That's sort of a broad overview of how the electronics works, and now I'm going to talk more about what we've got going on hardware. So the sort of phrase this? The fundamental part, I guess, of the machine. It all sits on these linear rails. These rails basically just... One moment. Ooh. Alright, I'm back. These... Oh, no, I'm not. Okay. So basically, this machine, it has... These are called linear rails. And there's a little sort of... It's called a block. And it sort of just rides along on here. And what's special is there's very low friction. There's basically no play, so it can't like wobble in any direction. It can only move this way. There's no other way it can move. And that is hypothetically parallel to this. In actuality, it isn't, because I'm a human. I made this. It's not going to be perfect. But it's essentially parallel to this. So this can slide back and forth on here. And so this is the x-axis, so it can move back and forth like that, back and forth like this on the y-axis. The y-axis has a bit more resistance, and I'll get to that later. And then there's also a z-axis, so that can go up and down. And yeah, just for reference, I'm going to go over that one more time. The coordinate system we have here, just Cartesian coordinates, but x, y, and z. It's not terribly important, but it's good to keep in mind. Yeah, and so you might be like, well, how do you, okay, cool, so you can have it moving around, but how do you drive that? Well, fantastic question. We have what are called stepper motors. Now these, they're sort of similar to it. If you think of it as a servo, you're not terribly far off. The biggest thing it's missing is what's called the encoder. And the encoder, it sort of makes like a smart motor. The motor knows where it is. This doesn't know where it is. So if the machine is like, I am at X10, and I just slam it that way, it's still going to think it's at X10. And as you can probably infer, that is bad. And that's what's called missing steps. The motor is going to be moving, but the computer doesn't know that it's moved. And so it'll basically, if it's cutting a circle like this, and I move the x-axis, well, it's going to be doing it over there, and just everything will be off. So now, assuming your machine is properly calibrated and you're not pushing it too hard or anything, you should not miss steps. If you're missing a step, something bad is happening. So, and this machine, it doesn't really miss steps. Because I do very conservative settings, not because it is precisely calibrated. But essentially how this motor works is, it's called a belt and pulley system, but it really is just a rack and pinion. And so I'm gonna sort of try and move you in here. I'm gonna cut. There you are. Okay, so hopefully you can see this. So there is a motor on the other side of here. You can't see it. It's there, trust me. And so it can spin. And one of the greatest questions of mechanical engineering is, how do we turn rotational motion into linear motion? This is one way to do it. This little thing has some teeth on it. This belt also has teeth on it. So when this spins, it moves it back and forth. So I'm gonna move the y-axis right now, and you should see that motor turn. There it goes. And so if this is sort of like, what, how is that working? It's essentially just a flexible rack and pinion. That's how I like to see it. Because it is just sort of a rack and pinion. It's a little different, obviously, but just instead of the rack, we've got this belt, and instead of the pinion, we've got this pulley. Alright, I'm gonna bring back out now. So that's the drive system, and that all the wires for that are routed through the machine, and also in these cable crawlers. Let's see, what else should I talk about? I'm going to talk about one more thing on the electronics, and then I'm going to talk about sort of how it's built. I want to touch on these limit switches. There's one there. You can probably see this one. basically those limit switches are positioned at the end of travel. So if I didn't have those there, it's going to keep going and keep going, and because I am only human, I make mistakes, and sometimes I will accidentally tell it to move somewhere that it's not allowed to move. There are ways to make it so that doesn't happen, but they're pretty involved, and I don't like them. And this solution is better, for me personally. Other solutions exist, but basically, if the machine goes too far, it's gonna hit this limit switch. So if it goes, let's say, too far to the right, this limit switch will get hit, and there'll be continuity. There's just two wires coming out of there that are run all the way through this tube, then through the cable crawler, then into the Arduino, and the Arduino will be like, oh shoot, the right end stop has been triggered, and it will like shut off the machine, and it'll be like, hey Van, like the limit switch went off. What the heck happened? And it'll sort of tell me off, and I have to fix it. But yeah, that's what those do. They're pretty useful just as like a safety thing, because if you don't have it, the machine can go yeah, it's not great. But yeah. Let's see, is there anything else? I think that's about it in terms of electronics. So the one last thing I want to talk about is sort of how is this thing built? Like, what have you made it out of? So it was made out of this aluminum tubing. You can see it. It's all beautiful. This is 1.25 inches. In his video, Ivan uses 30mm tubing, but that's sort of hard to get in the US. It's like, you can get it. It's a specialty item, so it costs a lot more. So Ivan made a version for us Imperial folk to use. They use an 1.25 inches, and it's just, what am I talking about? Okay, sorry, bit of a tangent there. It's held together mostly by threaded rod. So like, what you'll see, you can probably see some of the threaded rod poking out. The threaded rod just pulls it together. It's like a long bolt. You just tighten it up, and then it pulls the frame together. And so there's sort of these two squares, and then there's little sort of column bits, and that tightens it in the up-down direction. So you get what is a pretty rigid frame, and then that's all bolted down to this waste board. The purpose of this waste board is, as you can see, we can drill into it and stuff. So I can just screw my parts down. Obviously, there's so many ways to do work holding. Screws are just easy, cheap. It sort of works, and so we use it. But there's tons of other ways. One important thing to note: I did not build this off the waste board. The waste board is sort of a consumable. It doesn't have to be, but I'm gonna probably have to replace this at some point. So the frame gets its rigidity mostly from this aluminum. Some weaker machines will get some rigidity from this, but I trust the accuracy of this piece of plywood a lot less than this aluminum. I don't know if that's a good assumption to make or not, but that's why it's built off the frame. So I built this frame first, built all this, and then attached this. It's not terribly important, but it is sort of, yeah. Okay. What else is there to mention? This is just a standard wood router. Let's see, I guess technical specs if you're interested. This is GT2 belt, NEMA 17 steppers, just standard. The Makita RT0701C trim router. I'm running GRBL Gerbil on Arduino Uno with the latest, I think it's the 1.1 CNC shield from Electro. I think that's about it, technically. I'm gonna try and also link Ivan's video on it, so you can watch that. You'll get a better idea of sort of how it came together. I'm just sort of trying to provide like an overview of how we got to where we are now. So, I'm going to, I'll meet you over there on the computer and I'll talk about the workflow. Here we go. So this is my CAD program. I use Onshape. It actually works in my browser, which is pretty neat. But yeah, so here what I'm making today is this coaster for a friend. You can see it's pretty simple. It's just this hexagon that is, let's see, just so you have sort of a reference, about 18 mil thick. It's pretty thick, but it's because I've only got some pine sheet to work with, so it is what it is. And then we've also just got these letters cut in. So if you don't know what CAD is, it stands for Computer Aided Design. Essentially what you do, at least in this program, is you make a 2D sketch and then you would do what's called extruding to turn it into 3D. So basically I kind of drag it out. And then I do the same thing for that text. I just sketch it on there. And there are like a bunch of tools and methods you can do to get that sketch. Once you've got it there, you can just extrude it and extrude it out. Obviously there are a bunch of ways to extrude as well. This is all like pretty simple as far as like CAD goes. And then I just threw in some fillets. Those aren't necessary, but because of how machining works, like this corner, it can't be 90 degrees, at least with the way that I do it. Like, that is not possible on my machine with my methods. So it's not that the fillet is here also so I can really just see sort of like this is what it's gonna look like. Because if I did this, like I could get external corners because the bit can go like woo woo. The bit can go like this, but it's gonna leave a radius there. So I just put those billets on there so I can see what it looks like better. And then if I thought like this looks bad, I could try and rework it some. That's about it for the CAD though. I then just export it as a step to my CAM program, which is Fusion. So CAM stands for Computer Aided Machining as opposed to Design, which is what CAD is. And basically this generates what's called G-code. And G-code is what my machine can understand. It is telling it basically what places to move, when to move there, how fast, all that stuff. So in Fusion you sort of go left to right here along this toolbar. And so you start by making a setup, so we sort of tell it what the coordinate system is. I want this to be left, right, this to be forward, back, this to be up, down. And then I also am going to define some stock, so it sort of knows what we're making this out of. The actual piece of pine is bigger than this. It's sort of, we don't need to model in the entire thing. So we've just got this sort of rectangle around it, and it's going to remove some of that stock. It's not going to remove it all, it's just going to remove what it needs to though. So our first tool, and first off, this is what's called the tool path. It's just, not to be condescending or anything, it's the path that the tool is going to follow here. And so this one you can see here, this is called the pocketing operation, because it's making this pocket. You can see, will it let you? No, it won't let you see what it is, but basically we're just coming in here, going in, and then just going around, knocking all that material out. Okay, so that's the pocketing operation. That's how we're going to get our text for the coaster. Then we do what's called a contour. I'm sure there are lots of things you can do with a 2D contour, but they're very oftentimes used to cut stuff out. So we're just going like this. And you might be like, what are all these blue lines for? We're doing multiple depths, basically. My tool and my router, my machine as a whole, is not capable of making this entire cut in one go. So it does it in a bunch. I could maybe do it in less than this, but it gives me a nice finish and it works. So I do it. Oh, and one last thing of note. These little things right here, that's intentional. Those are called tabs. Basically, they keep the model in place the entire time. So even once we've finished it, it's still locked in, because like basically we have like screws like here and here and here and here and whatnot. If we didn't have these tabs in here, there would be nothing holding this in place, and it would rattle around. It would hit itself up against that bit. It could hurt the machine, but it's more likely to just hurt the piece, and that would look bad, and it's not dangerous, but you don't want stuff like that happening because it's unpredictable. So I'm not very good at explaining things, so Fusion can simulate the toolpath, so I can just show you the entire toolpath. So I'm gonna click start. And you can see it goes in, and then it comes around and cuts everything out. Okay, and then now it's going to do this contour toolpath where it just cuts everything out. And right here you see it kind of comes up some. Here, let me slow it down. Okay, a little faster, bud. Come on. And basically it's going to do that to clear chips, clear dust. It also gives me a good chance to come in with the shop vac to sort of get some of this stuff out. Because it's wood, it's pretty generous. Like if I was machining like aluminum or something, it would be a lot more important to get these chips out because they could clog up the bit. But because of the way this works, it basically just turns into like a dust. And it's okay for the machine to do it again, but it's still good practice to clear it. You don't want all that sitting there. So it's just going to keep going, cuts everything out, there, and it's done. You can see we've still got our tabs in place. This green stuff is the stock. And yeah, that's about it for the sort of the workflow from idea to CAD, where we model it, then to CAM. And then last, what you do is actually I'll go over one more thing. We do what's called post-processing, which is this, and you can see here, I'll just go ahead and post it. Sure. And then you can see this just generates all of the G-code. So this is basically what the machine can understand, so it knows what to do. Alright, and then after that G-code, we just use the G-code sender to send it off on its way to the machine. And yeah, then we get a part. That's about it for the workflow. I'll see you back in the machine. One last thing before I go back to the machine to recap. These are the coasters I was making. I made 3 of them. They're hexagons. The wood has a bit of character in some places. But yeah, the only finishing I did, I sanded just a little bit. It comes out of the machine really clean though. I just want that to be uniform, and people are using this, so even if there's just one like splinter or whatever, that would be bad. So I sanded them, and then I used a blowtorch to burn the wood. I'm still not certain if I like it or not, to be perfectly honest, but it gives it some contrast, which is nice. And then I just used Danish oil to give them their sort of the color. If you see the wood in the video, it's much lighter. Alright, I'll see you in a sec. So I just showed you the sort of the CAM process, what happens in CAM, as well as CAD, and then I also should have shown a very brief video of it cutting. That part did actually fail due to operator error, but I still got some more that worked, so those are going to be going to their owner in a few days. I think tomorrow. They're drying right now. I put some finish on them. But I wanted to really quickly talk about my experience with this project and how it sort of reflect on it, because this has been sort of my second big project that I've done essentially solo. I had obviously people like help me like online and stuff, and like forum answers as well as like Discord stuff, but I didn't have like a partner for this, I guess you could say. It was just me. So if you've seen my Drift Strike video, that was recorded probably the most enjoyable part of that project. That project was awful. I didn't know what I was doing, which I think most challenging projects, you don't know what you're doing, but it was done in a way that the documentation just wasn't there. I really like Colin Furs, but it just wasn't documented. So it was really, I was never confident if it was going to work. I didn't have anyone with me like throughout the project where I could be like, hey, is this a good idea? Am I going down the wrong road? Like, is this a good way to do this? And so it was a lot of just guessing, and frankly, I'm not gonna say I lucked my way into doing it, but I definitely think it could have just not worked for a lot of reasons, and there were points where it was sort of just like, I got lucky. I think you get lucky in all projects, but that one especially, it was a lot of, I just wasn't pleased with it. It was just really hard on me personally. But this project was sort of, I mean, it wasn't the polar opposite, it was still really hard just because of the scale of it. I'd never done anything like this before. And I think similar to that is like, there was a very large financial aspect to it. Like, I can't really afford for this not to work, if that makes sense. It's something like the air can or whatever, like that's $50 a PVC. Like, if it fails, like, wow, that sucks. But if this fails, like, okay, like, what do I just can't really grapple with how that would look for me, if that makes sense. But I think that the biggest difference I want to touch on is, well, there are two things. So basically, Ivan did, when you're comparing it to Colin Furs' documentation, it sort of seems insincere to compliment it, but it was really good in my opinion. There were full CAD files, a full VOM, a brief README that was helpful. I mean, a lot of it was sort of doing it yourself, but there was also like the full build video. And also, a big thing is once you get past the physical assembly, the electronics is very much like something that is covered. Like, how do I set up a CNC router in Gerbil? I know it sounds like a very specific topic, but it is thoroughly documented. You might have to look a couple of places, but it is something that has been done many times, which I think took a lot of the stress away, because I knew I was doing something that other people had done, and so I knew, well, okay, this is going to be possible to an extent. But easily the large, okay, one moment. Oh, shoot. Oh, okay, 4 minutes, yeah, we're fine. Alright. Okay, I'm back. I think the largest thing, easily, was, Ivan set up a Discord server. He had his Patreon Discord server, and he set up a channel for the CNC router guys. And so there were, I'm not sure, there are at least 10 of us right now who were working on, we're all sort of in, there are a couple guys who have finished, there are a lot of guys who are just getting started. I think just last night there was another guy who got in and was sort of asking questions, like he had decided that he wanted to do it. And it was just having someone who knows more about it, where I can just ask my silly question. I can be like, is this a bad idea? And like 90% of the time they're like, no, that'll work, that's fine. This way might be a little bit better. But there was also that 10% of the time where it's like, no, don't do that, like that'll break everything. I'm like, oh shoot, okay, thank you. and it's hard to express just how much stress that took away. Like having somewhere I can be like, here, look at my build. No, yeah, that looks cool. Like everything looks right. I think it just made it made it easier. I can't speak to necessarily how much better or worse the final product would have been without them, but I can tell you that it made it just far easier on me personally, having someone that I could talk to about it. I think that's something I really take for granted in the in the Sigma Lab. It's just a bunch of smart people who know and can understand to an extent what you're working on. Like the stuff we make in the Sigma Lab is pretty cool, and unique, but a lot of it is sort of, I mean, there are a lot of smart people there, so they can be like, yeah, that's, they can help you troubleshoot and stuff, and I don't really have that. And sort of like, I can't really there's no guaranteed person I can reach out to, and so having a group of people that you can talk to was just incredibly helpful. I think that's about all I wanted to say about that, but thank you to Ivan, thank you to the guys in the Discord server. If one of you somehow managed to find this video, you were an incredible asset. Other things to touch on. Cost, maybe if you're interested. Ivan's came out to about 600 euros. I'm just not sure how much mine costs, frankly. I tried to keep track of it, but there's just too much, and I just lost all motivation to try and keep track of that. It would be in the, probably between $1,000 and $1,500. I'm guessing the lower end of that. And that sounds expensive, and I mean, $1,000 is a lot of money. But for something like this, that's actually a really good deal. And I mean, I intend to, if I stop using it, try and sell it or give it to somebody, or it wasn't just like a fun little project. Like, no, this is a tool, this is an investment, this is something that I will use. And if I stop using it, hopefully someone else can use it. And worst case scenario, there's valuable stuff on here. There's a lot of cool stuff I could use. I think that is about it. Thank you if you actually watched the whole thing. That means a lot to me. I know I did a really poor job of explaining everything. So if you have any questions, please just leave a comment. It pains me every time someone leaves a comment. So just please do that. Let me know. I can try and answer that. Yeah, but thank you everyone. Thanks for watching. Thanks for sticking around. I hope you have a great new year. Bye bye.